Okay, so thank you for the introduction. So the basic motivation of this talk is flush and reload and flush are kind of a great attack primitive that we've already heard mentioned several times today. So if we take, but they're a decade old. So if we take this graph up there, we have this timing histogram of how long it takes to flush a cache line. And so just for those who are not used to that, in CL flush is faster when the thing is not in the cache. So your cache misses are faster than your cache hits in blue. But basically, modern systems are a little bit more complex than this nice little histogram. And so if we try that on a multi-socket system, and we intend to do that on let's try cross-socket attack, because CL flush does flush across socket, we get this kind of histogram. So above you have flush and reload, below you have flush and flush. In both cases, these are not exactly nice histograms, and you can't just pick a threshold and distinguish stuff, because you have fast and slow hits that are messed up. And so generally, the idea of our work was to try and update the paper and figure out what works and how can we make it work. And so we have this little table of what is kind of known when we started. So flush and reload, basically, we know it works very well on single-socket Intel and AMD system. We definitely don't know much about multi-socket system, and flush was demonstrated on Intel Skylake CPU and earlier. We do have to update that. We discovered more recently that somebody also demonstrated flush on Ventu. But so basically the goal was to cover these two areas and determine what is going on there. Why exactly is this a little bit messy? So this is, let's consider what do we have in a NUMA system. So we have the silicon block on which we have a CPU core. It has some private caches, and we have more of these with more private caches. And then we have some sort of interconnect and a distributed last level caches, which nowadays is not inclusive, and so you also have a cache directory for cache coherence. And then you have a DRAM and you have some interconnect. And then we have a second copy of all of that in our system, and with connected, and with another DRAM. And obviously, if you are a core, let's say on the left, and you're trying to access the left DRAM, it is faster than a core on the left trying to access the right DRAM. And so the time you need to access memory is different, and so we actually group the core in our system with the memory controller into groups that we call NUMA node that basically tell you these set of core are closer to this memory controller and schedule things in order to schedule things cleverly to optimize the latency or optimize the bandwidth. One fun thing, though, is you have many caches, and they all have to be kept coherent. And so basically, this involves both per-socket directory and some cross-socket communication, which makes things more complicated. And so typically, let's say I'm the attacker. I'm on this little core on, I'd say, your left, yes. And my victim is on the right core. And now if I move, I get one set of transition. If I move my victim to the right core, as we now see, suddenly the set of transition is different, and same thing if the memory I target moves from one core to one memory controller to another. So this obviously changes the dynamic. And so what do we call a topology unaware attack? So if we basically build our histogram weighting equally all the possible attacker location, all the victim and all the target location, then this is what we get for flush and reload. Unfortunately, in this, we can't find a single threshold that will work for everybody. On a simpler system, you could do this histogram, pick one threshold, and on one side you have all the hit, on the other you'd have all the misses, and your attack would work very well, even if the kernel migrates stuff around. But here, if the kernel starts migrating stuff around, your attack is kind of dead. So the next thing we can do is just take into account the socket and the NUMA nodes. And so if we do that and we split our histogram according to the attacker, the victim, and the target memory sockets, or NUMA node, we get these kind of histogram. There's four other ones that are basically symmetries, so identical to some of them. And in this case, we already get a significant improvement. And in 3 cases out of 4, we can actually pick a good threshold and it will work. And we still have one edge case. And so what happens if we go further, what we call a topology-aware attack, basically take into account the precise core location of the attacker, of the victim, and also of your take more into account more fine-grained data info about your target that is trying to basically account for cache slicing. Because we saw that L3 is distributed and has slices. And if we do that, we get many histograms, but that look much sharper and more precise. And this is a model, if we actually can put ourselves in one of these histograms, we can probably run a very effective attack. And so in summary, the conclusion that we have is if we take the table that we had initially and fill it in with a new value, we can run like the topology unaware attack on single socket Intel client. For flush and flush, it also works on single socket servers. However, flush and reload in single socket server CPU doesn't work very well in topology aware setup. If we add NUMA awareness, we get Intel multi-socket server and for both attack and AMD multi-socket flush and flush, not flush and reload again. And for everything else, we actually need to go to a topology-aware attack to actually start to have clean enough histogram to hope to run a reliable attack. And we also figure that flush and reload doesn't necessarily work as well as commonly admitted on some of the most recent machines in the area where we expected things to work. So one first conclusion is these systems are complex, so topology has a large impact. The second conclusion is the kernel can mess with you, so you need to make sure the kernel isn't moving stuff around behind your back while you're trying to run your attacks. Otherwise, you will get into interesting headaches. And then flush and flush is not also ran insignificant thing. It is a primitive that is worth studying in its own right because it can be better than flush and reload, which is useful. And we get a new optimized covered channel that, if we could talk about that, but that is a side note. Future work, we want to use the data to reverse engineer. We have a single 4-socket machine gave it 80 gigs of data. So we have lots of data on all these machines. One thing also is there are a couple instructions that use the same threat model, which use typically the prefetch for write instruction on Intel, which we would also add to the stable. And then one goal we have is to build an end-to-end DVFS robust attack, which would be a collaboration with a few other people in the room here. So thank you for attention, and I open the floor for questions.
Yeah, thank you very much. One question? Yes, maybe? Okay, why don't you tell us what is load, flush, reload?
Oh yeah, I happen to have a slide here that was cut out. So the idea is, so on the right side, you see basically the cache coherence transition in both attacks. So if you take the flush and reload attack, you have your start, which is kind of initially in the invalid state after you flush it. And if the victim does, or the sender does a load, you move into exclusively held by the victim state. And then the attacker does a load, and you move into a shared state. Meanwhile, if the attacker does nothing, you stay in the invalid state, you move to exclusive state. And so what you're comparing is how long does it take to load something from exclusively held in another core, and you compare this to how long it takes to load from an invalid state. So you're comparing exclusive in another core and invalid. In flush and flush, you're looking at how long it takes to flush in the exclusive state in another core and flush an invalid line. And this new primitive basically has the sender either do a flush or a load. So the sender actually does a flush, and that is why it's only a covered channel, because you don't find random victim doing flushes depending on secrets. And so what you end up comparing is if the sender did a flush, you load from an invalid state. If the sender did a load, you basically set up this line in the shared state because you previously did a load, and so you're comparing shared load with invalid load, and this actually has a much bigger timing difference than comparing exclusive and shared. And this makes the attack much less noisy, even in these complicated multi-socket systems. However, this obviously assumes you have a victim that actually is cooperative, which is why it's only a covered channel. So thanks for your attention.
Thank you so much.